Hello and welcome to the Scenarios MCVT Integrated Model Simulation tutorial video. In this video, we will briefly explain the structure of MCVT, demonstrate the process of downloading the integrated model from GitHub, and also demonstrate running a scenario simulation in MATLAB and Simulink. The Modular Coupled Virtual Testbed, or MCVT for short, is designed to represent a notional real habitat consisting of various systems and human or robot agents. Subsystems such as those you see in the notional real habitat figure, including the structural system, power system, environmental control, and life support system ECLS, and a command and control unit, are examples of systems that are expected to be established in a deep space habitat. All these subsystems are closely interconnected, and its modeling concept is approached as a system of systems to study their dynamics and interactions comprehensively. Each subsystem can operate independently, while its combination with other subsystems establishes an extraterrestrial habitat as an integrated complex system. Modeling a multidisciplinary complex system with different interactions and simulation requirements is a challenge. To better manage the data exchange among subsystems, the system interdependencies are categorized into 4 types. Physical interdependency. This type of interaction exists when 2 subsystems share a physical link. Examples of this interaction are sharing boundary conditions such as pressure and temperature, or power supply from the power system to the sensors in the habitat. A cyber interdependency exists when 2 subsystems share an informational link. It includes a power request from sensors in the habitat to the power system, or a report on fault detection and diagnostics information from the system autonomous sensors to the command and control unit. An intervention is an action taken by agents or the health management system to improve subsystem performance. An intervention can be physical, like sending a robot to clean a solar panel, or it can be cyber, like changing the set point of temperature control in the ECLS unit. And finally, disturbance. It includes all the external excitations and loading conditions from outside the extraterrestrial habitat. These interactions are physical outputs from the exterior environment to the rest of the habitat systems. The conceptual space habitat was mapped into defining functional requirements and broken down for subsystem modeling. At its current stage, MCVT consists of 7 subsystems: command and control or health management system, a structural system, power system, ECLS, agent system, interior environment, and exterior environment. MCVT is written in the programming language and numeric computing environment, MATLAB, and the MCVT subsystem models are also built on MATLAB's graphical programming environment, Simulink. On your screen, you see the highest modeling level of MCVT in the Simulink modeling interface. It has 6 subsystem blocks representing the 7 physics-based models of MCVT: structural system, power system, ECLS, interior environment, health management, and robot-human agent. In this case, 2 MCVT subsystems are represented in one modeling block of the integrated model, and the exterior environment. All the interactions are rigorously handled within the coordination block on the left-hand side of the screen. Each subsystem modeling block receives input signals categorized in our 4 interdependencies: cyber, physical, intervention, and physical disturbance from the exterior environment. Likewise, each subsystem provides output signals that are cyber and or physical. Additionally, a fault detection and diagnosis, FTD, signal is said to be an output of each MCVT subsystem. FDD aims to monitor the health states and performance of a subsystem. Suppose a fault or damage occurs at a particular subsystem. In that case, the FDD block within that subsystem should detect the fault, diagnose the root cause, and quickly notify the intelligent health management or command and control system. Likewise, if the system recovers by the appropriate level and type of intervention, the FDD block should detect it as well. Now we will move on to running the MCVT integrated model in MATLAB and Simulink. But before we start, make sure that you have installed MATLAB 2020A or a newer version in your computer. If not, you could download it from the link shown on the screen with your academic credentials or contact the IT department of your research institution. Also, make sure that you have installed Simulink. Usually, it is a default download required when installing MATLAB. However, it is always good to make sure that you select Simulink as a download option when installing MATLAB. After installing MATLAB, and even if you already have MATLAB, check that a proper compiler is installed. To check the currently installed compilers on your PC, you can go to the command window and type max-setup. If you have compilers installed, you will get a list of compilers available on your PC, as in my case here. But what if you do not have any compilers? If after running the command max-setup, you get a message saying no supported compilers found or no compiler found, you can install the MinGW compiler in MATLAB, available at no charge for Windows users. In the Home toolbar, click on the Add-ons icon, and the Add-ons Explorer should open. In the search bar, type MinGW, and here it is. It is the MATLAB support for MinGW compiler. Let's go ahead and click on it, and you should be able to click on install and install the compiler. It might take a little while, and I will go ahead and fast forward the installation. We're back, and the installation was complete. It would be best if you rerun the max-setup to make sure the compiler is installed successfully. We typed max-setup in the command window, and we see that the compiler is set up. If that is not the case, then restart MATLAB. If you are a Mac user, then please install Xcode 12.x or a later version. Before running the MCVT model, you should also make sure that you have specific toolboxes. In the Home toolbar, click on the down arrow on the Add-ons icon and select Manage Add-ons. It will open and show the MATLAB toolboxes that you have installed on your PC. Make sure you have the System Identification toolbox, the Statistics and Machine Learning toolbox, the Signal Processing toolbox, the DSP System toolbox, and the Control System toolbox. If you do not have them installed, click on Get Add-ons and it will take you to the Add-on Explorer. You will search for the missing toolboxes and follow the same steps as when we installed the compiler. To download the MCVT model and codes, you must be granted access to the RETH drive in GitHub. In the GitHub repository, you will find the latest version of MCVT. The link to a detailed manual for the use of the MCVT code and simulation, and also the design structure matrix with the system interactions. When you sign into GitHub, you are able to download or clone the MCVT repository. In this case, we will download it, but you can clone it if you wish to as well. We download the zip folder of all the MCVT codes and models and save it in a place that you know you can easily access and wish to run MATLAB from. In MATLAB, we will click over the Browse for Folder icon and search for the folder that we downloaded and unzipped from GitHub. Once we find it, we select a folder, and in it we will find all the MATLAB files that we need to run MCVT. To make sure that we have set up the MATLAB environment correctly to run MCVT, we will run a quick example and open the MCVT run quick check script. In it, you will find different model parameters that are used to run the simulation, such as total simulation time, mirrored impact time, mirrored impact location, dust accumulation input, and other input parameters for the different MCVT subsystems. And I will encourage you to go over the integrated model code manual, where you will find details about these parameters and what do they do to impact the simulation, how do they change it, and you will find a very descriptive explanation on what is their impact on the MCVT integrated model. But for now, keep all the parameters unchanged and run the simulation to make sure that everything's running properly. Click over the green play button in the top of the toolbox and run. We will check the printouts in the command screen and make sure that they're the same as the ones specified in the code manual. And we see that it says execution starts, so it has started. Meteorite impact should happen, it happens, and we have the dust accumulation start due to meteorite impacts, and then it starts due to engine exhaustive events, followed by execution completes, and the execution time was 25 seconds, which is around the 30 seconds that this simple example should take. So you see that this runs correctly, so the simulation is running correctly. Now we close the run quick check MATLAB script because we learned that everything is running properly, and move on to running a scenario example. So I'm going to go ahead and clear all the variables and close the script, and now I'm going to open MCVT input file. The MCVT input file, it's where all the variables in the script are set to be specific values, and by default you would find all the nominal values specified by the model developers and also in the model code manual. So in here you can set the execution time, also the different scenario input time and input specifications such as dust accumulation. And here we have the damage ID case, which is set to 4, and I'm going to go and change it to 1. So see, you can also do that, and I'm deciding that I will have a scenario with minor damage in the protective layer. And then you will find the rest of the parameters for the MCVT subsystems, which I'm going to leave as default, and save this script. Now I move on to the main file for running the simulation, which is MCVT run scenarios. And in here we run the simulation, but if you see in the load simulation parameters section, there is a file that is called, which is MCVT simset. I go and open it. In this file you will find the integrated sampling frequency for the whole system and also for the individual system sampling frequencies. It says that this portion of the file should not be modified, or this portion of the model of the MCVT should not be changed, so we're gonna leave it as it is. It also calls on the individual system simulation scripts. So I'm gonna go ahead and leave it as it is and go back to my MCVT run scenarios, which after calling these two scripts that we went over, input file MCVT simset, it runs the simulation. And it runs the simulation by calling on the MCVT integration Simulink model. and you see that even it is specified simulation mode of normal. So we're going to go ahead and open the MCVT integration Simulink model. We look it up in our menu for the current folder and we open it. So by default it opened at a lower hierarchy model, so we're going to go and click on MCVT integration, which is the highest hierarchy model found in this graphic interface of Simulink. So you will find the 6 subsystem blocks that we went over briefly in our introduction for MCVT, and we're going to go ahead and open this structural subsystem. And in here you see that we find the structural subsystem with inputs and outputs and different specifications. And if you go inside each of the subsystems, you will even find more detailed models of what the structural system is about. So for now, we're just going to focus on this highest hierarchy of the structural model. You see that we have cyber systems. In this case, there's none to the subsystem of the structure, but you do find disturbances, physical inputs, and intervention. Also, you will find that we categorize our outputs as we went over it with cyber and physical. And we also save these outputs for the whole simulation time in a mat file that we can access later in our code. So now we go back to MCVT integration with all the subsystems, and you find that all of them follow the same architecture or similar to the structural subsystem. Then we go to the interconnection block that if we click inside, you will find the exchange of signals from all the subsystems and how they go from each of them to others and they're categorized. And I encourage you here that if you want to know more details about this data exchange, to look up the design structure matrix and learn a little bit more of the interfaces and interactions that they experience with each other. So that is the Simulink model, briefly going over it and just looking of what it takes. You can also run it from here, but it is preferred that you run it from the simulation script in MATLAB. So now we're gonna go ahead and run the simulation, the scenario that we specified as one, and you're gonna see in the command window the printouts of what is happening in the simulation. And I'm gonna go ahead and fast forward the simulation because it takes around 4 minutes, and we will get to our results part. So now we've completed the simulation and you saw the printouts in the command window. I'm gonna go ahead and move the plots that we generated. You can see that we have agent position, command memory state, agent action ID, the nuclear radiator clean, the solar panel clean. You have power storage status, also power supply to the different subsystems, the egress air supply, air ventilation, heating energy, cooling air temperature. These are some of the outputs of the subsystems. I'm going to go ahead and close them. You can look them up when you run your simulation in more detail and also refer to the manual. Then now we have the interior environment temperature measurement, the pressure measurement, the interior wall temperature from the structural system, and also the wall pressure, outer wall surface thermal boundary, inner wall surface thermal boundary. Also we have the dust accumulation rate, impact indicator, ground motion from the exterior environment, damage detection results, the solar flux for egress and power, and for the structure. And you can look them in more detail when you run your simulation. And as I said before, refer to the manual as well. And how did we generate these plots? Well, in the save data and plot results part, we call on the MCVT plot data script that you can open it up, and you will find that we call on the mat files that we saved in the Simulink folder with the time history that you saw plotted. And here you can call on the different outputs that each subsystem generates, and you can see that you can call on cyber, outputs such as damage probabilities, and also physical outputs such as an exterior wall surface temperature. You can go into your time history data that you saved and find out other outputs that you wish to also plot. In this example, we run case number 1, and you can go ahead and change the damage case to number 4 and see how that affects the performance of MCVT and what differences you see, or whatever suits your research question better. And we save the data in specified folders by run, number, and also date. And if you run something in the same day, then you can go ahead and change your output folder name in the MCVT input file, put run number 2. And if you want to be more specific about the case that you're running, you can go ahead and write case number 4 in this case, and save your data in a more efficient way. And in that way, you can run the scenarios. I hope that you find this video useful and you're able to run MCVT in a more efficient way.